All right. I do not know how many people have seen the talk from Osmo DEFCON. It's going to be pretty similar. I exchanged and added a few things on recent work other people have done on top, and yeah, hopefully there's something new for everyone. Yeah, I'm going to talk about transmitting radio signals. Yes. Font size. Yeah, it's quite big. Better. Okay. About transmitting radio signals with VGA adapters, and this idea is quite old. I again looked at what were the origins actually, and it goes even back further than I mentioned in the original talk. It all started with a paper from Marcus Kuhn and Ross Anderson, and it's a pretty interesting read because what they did is everyone knows Tempest probably. Basically, you can receive the EMI caused by CRTs or LCD screens, and they actually applied some tricks with hue and saturation and so on, that the signal you receive on the Tempest receiver is different than what's actually displayed on the main screen. So that's quite interesting, and this sparked a whole lot of other people experimenting with it and transmitting AM radio, and then at some point in 2005 DVB-T and analog TV. And so there's been some previous work on this, and a very similar idea is, which is probably broadly known as RPITX, which uses PWM to transmit radio signals. And just recently I also read something about FPGA. I think it was even ICE40 PWM being used to transmit radio signals. So yeah, there's lots of stuff going on. But when you use a VGA DAC, you have one problem. Typically, like also analog video, there's a synchronization period and the blanking being done. So there's horizontal synchronization, there's a small pulse, which on the old CRTs basically happened during the duration where the cathode ray is traveling back at the end of each line. And there's also a vertical synchronization period where the cathode ray would travel up from bottom right to top left again. And there the VSync H-sync signals are outputting a pulse, and the DACs are just blanked during this period, which you can see in this picture here. And yeah, if you would use that for transmitting radio, you of course have lost samples which you cannot control, and which distorts your signal. And for OFDM, it sort of works because you integrate over the symbol duration. So when Fabrice Pilar did this DVB-T transmission, all the forward error correction and so on could handle this. But he didn't really figure out how to disable H-sync or V-sync. And I came across, I was looking for obscure hardware on eBay and AliExpress, and I came across those USB 3 VGA adapters, which said, well, you need USB 3 to support the full resolution. And otherwise it will fall back to 800 by 600 with USB 2 interface. And there were videos on YouTube showing that it doesn't work really reliable on all machines, and that there's flickering on the screen and so on. And I thought, well, this sounds interesting. Probably, they do some software-defined VGA, and this is the case. So there are actually two VGA, USB to VGA and HDMI manufacturers. So one is DisplayLink. They have the very classic approach, just a GPU with USB interface. They have a external memory chip where they have all the frame buffer, and so there you do not have this issue. But this company called fl2k did a completely software-defined approach. Of course, they save the external frame buffer memory, so they have a single chip solution, which is very cheap. And they just use USB 3 and constantly stream out the image, and the frame buffer is actually in host memory. Those devices look like this, available in many form factors. There are also ones available with DVI output and HDMI output and HDMI and VGA. So there's 2 variants of this chip, 2 packages. And this is how the fl2k FL2000 hardware looks on the inside of those adapters. In this case, you also can see an SPI EEPROM or flash, which in this case is an 8 megabytes flash which holds the Windows driver. So it also doubles as a mass storage device, so you do not need to download some driver from the website. It's on there, but typically the cheaper versions of those adapters do not have this flash because, well, it costs money, of course. Yeah, but otherwise it's very simple. There's some filtering going on, and 2 voltage regulators, and that's about it. So yeah, when I received those devices, I wanted to take a look at it and started reverse engineering it, and I took the same approach as with RTL SDR, and you can do the same with about any USB device, actually. It's quite easy. I had a VirtualBox VM with Windows, which ran the original driver. Then you sniff the traffic with Wireshark on the host machine. And then you can start to replay those commands in the libUSB-based application. And actually, there's a nice tool, which I already used for RTL SDR back then. It's unfortunately unmaintained and from 2011. I have the link at the bottom. And this is a small Python guy, which can load a pcap file. And you basically can select the packets you want and do right-click export libUSB code. Quite nice. And yeah, then you at least can replay the USB traffic, and of course, then you have to identify the register rights actually required, and then comes the part to figure out what the registers actually do, and fiddle around, flip bits, and see what happens. So what I did is I tried to figure out what the data format was used in the USB buffer. It's not top left pixel and then continues linearly like that, because they use actually SSE and MMX optimization in their Windows kernel driver to send out those the frame buffer memory. They have some packed buffer format, which is not straightforward, but it was quite easy. Just display a large image in the virtual machine with just 1 pixel being read, and then look at with Wireshark at the traces and figure out what is what. And what took quite long is to figure out what the PLL registers in this device do, because the Windows driver just has a large lookup table for all resolutions and refresh rates, and then just chooses whatever is set. And so you do not get to know how the PLL values are actually calculated. So I really had to attach an oscilloscope, look at what comes out of the device, and then play around with the values in the register. And then I see, okay, this is a divider, this is a multiplier, and so on. And after quite some experimentation, I ended up with this. I could disable the the H-sync and V-sync on this device, and there was still a very small H-sync gap, like I think 6 or 8 samples. This is a not so high bandwidth oscilloscope, so you, yeah, as you can see here, but there were samples missing in the middle, and after further experimentation, I found out why that was, because I, of course, used the highest resolution this adapter can do, which is full HD, and but for this case, the ERP size, or the one whole frame gets split up in multiple transfers on the USB bus, and in this case, the last ERP or packet didn't have had a different size than the previous packets, and this didn't work out with the FIFO inside the device, and thus there this small gap. And so I looked at all the resolutions this device supports, and there's actually a few which are an even multiple of the USB super speed ERP size, and so I'm just using 1/80 times 124, and you end up with a roughly 4 megabyte buffer for one frame, and there's no more lost samples, and you just have a plain 3-channel 8-bit DAC with USB 3 interface, which can go up to 150 megahertz sample rate. So the outcome of all this was lib osmo fl2k, which initializes the device and sets the sample rate, and you can feed 8-bit signed or unsigned samples. Then this buffer format is converted, and it can use zero-copy transfers if the Linux kernel and libUSB support it, to basically reduce USB load. And someone also wrote a GNU Radio sync for it, with some modifications inside the library to use I and Q interleaved, so he's just using 2 DAC channels. But this is only interesting if you attach some IQ modulator. So the library comes with several applications, like analog to RTL SDR. You have a fl2k file, just streams out a file. A TCP application where you can use the old TCP sync in GNU Radio to stream directly to the device, and an FM modulator with RDS support, which is integrated from another project. Someone wrote an RDS modulator for this Raspberry Pi TX. And this can be used together with SOCKS to transmit wideband FM. And a test application, which is quite useful if you want to calibrate the sample rate of the device. You can measure what the actual sample rate is, and but typically the oscillator in there is plus minus 20 ppm. And as you have such a high sample rate and need to resample anyways, you can correct for this. So they're using the harmonics of the DAC. You can transmit quite a few standards without problem, at least if you are within a couple of meters of the device. So of course, wideband FM, which is probably the easiest with HD radio. There's also a GNU Radio block for that. DAB and DVB-T works, and GSM as well, with samples generated by Osmo TRX, UMTS and LTE. And what was most surprising is even GPS L1 at 1.5 gigahertz. So you have to be really close to the device, but you actually get a fix. And yeah, so you can spoof any GPS location to the device. And yeah, someone recently built a frequency marker generator for the whole AM band. So the device is transmitting basically the whole AM radio band, and at every frequency you get a voice telling you the frequency. So if you have some of those old AM radios, you can tune through and and yeah, receive this. And for GSM, I just upsampled with GNU Radio. The synthesized carrier frequency in the samples basically is 40.6 megahertz, and if you use a DEC sample rate of 138 megahertz, you get the first image at plus minus the carrier frequency, third at 414, and so on, and then the seventh harmonic is actually 925.4, which is AFKIN 976. So yeah, you see the signal on a phone. So this is the Osmo monitor tool. You can see the device is actually without any antenna, just right next to the phone, and it's because it's not properly shielded, and so it just leaks out a bit of energy, and you can see it on the phone. And now it's too big. I also did some tests with an Agilent analyzer, and I was surprised. It's actually looking quite good. The phase error of 2.11 degrees. So in this case, I desoldered the 10 megahertz oscillator on the VGA dongle and directly input the reference clock from the Agilent analyzer, so that I have a stable oscillator. But yeah, looking quite good. And this guy who built this radio frequency, this AM marker generator, also did some further experimentation with the fl2k dongle, and measured with the spectrum analyzer. And he noticed that you have this zero order hold effect, because the samples by the output by the DEC is basically a staircase. There's no reconstruction filter, so this is called a zero order hold, because the last sample level is being held until the next sample. And yeah, this gives you this filter effect that the yellow trace is actually the frequency response of the DEC with I think the sample rate in this case is 8.192 megahertz. So this is down here somewhere, and so you get this response. And he implemented a equalizing filter, which is the purple trace. So that you can actually, which is useful especially at low sample rates, that you can equalize this effect. If you use high sample rates, then you get this always from 0 to your sampling frequency. Then it's not as extreme as here, but if you use lower sample rates, this is quite helpful. Further ideas are to connect an IQ modulator to two of the DEC outputs, but unfortunately IQ modulators are quite expensive compared to the device itself. So probably some low IF approach would be better, but unfortunately there aren't also many cheap devices available. So I continue looking, but maybe something comes up. And one useful case would be, of course, to just add a reconstruction filter and use it as a configurable lab signal generator. I mean, you have 3 channels, and you can output 0 to 75 megahertz. And if you do not need 8 bits, you can actually, there's an RGB 332 mode where the device can just needs 1 byte per pixel, and then you can crank up to 450 megahertz. So you also could implement, stuff like Ethernet. I just recently did a small proof of concept. I implemented 10 megabit Ethernet bit banging. Should also work with 100 megabit, but there's a bit harder to debug because there's a scrambler in front of the output. But I also want to try this. And in theory, also the gigabit Ethernet should work, but yeah, then it's really hard to debug. And of course, one idea is to synchronize it with RTL SDR to use it as a cheap transceiver. I already did some experiments with that, at least for clock synchronization. So I used a stable 10 megahertz reference for the fl2k and used one of the DAC channels to output 28.8 megahertz and added a low-pass filter and then directly clocked an RTL SDR from it. And this works, but there's lots of phase noise I see. So there's still some improvement. Probably my filtering was just a quick hack on the desk. So I need to recheck the clock level to the RTL SDR and so on. And you then could use yet another of the DAC channels to feed into the RTL SDR. Because you have 2 ADCs on the RTL SDR, and on most of the RTL SDRs with R820T tuner, one DAC is unused, and you can switch them around gaplessly. So the idea would be to use a dedicated synchronization connection from the fl2k to the RTL SDR to look for output a pulse on the fl2k and then measure the time or the amount of samples it takes, so you can sync them up. Yeah, so that's it from my side. Any questions?
Okay. The need to synchronize the clock reference, for example, to have a transceiver with the fl2k in the TX and a Realtek in the RX, this need for synchronization is more for use, for example, in GSM, or because, for example, to use in trunk radio, it would be enough. I mean,
yeah, sure. Mainly for all TDMA-based transmission standards, because if you just use for trunk radio, or just do just a simple OFDM channel in one direction and on another frequency in the other direction, then you do not need any synchronization, of course. But for GSM, for example, or all other TDMA-based standards, you need, of course, synchronization. Yeah.
And the power output, sorry, I lost the very beginning. For example, at 100 megahertz, the power output you can
the power level is quite low, but of course you can add filtering and then amplify it again. But
But how low? 0 dBm? How low is the output?
I think I have thrown that picture out. Or we should also see here. Let's see. I think he also added a filter. Yeah, but it's around 0 dBm, a bit less. But yeah, You actually can combine the DAC channels, of course, for more output power. So they are matched to 75 ohms, but yeah, you just can send the same data, and I don't know. You of course then need to take into account the delay of the traces and so on. But yeah, it works.
Any other question? How much have the dongle prices risen since your first?
Actually, they didn't. So apparently they are so widespread that they even became a bit cheaper, I think. And actually, the same happened back then with RTL SDR. I think there was a short spike in prices, but yeah, it got cheaper. Yeah, of course. If somebody doesn't manufacture it anymore, yeah.
That's the problem when the chip gets end of life. And also, Osmo fl2k has not been presented at the CCC Congress. So.
Yeah. Right.
No, I don't think so.
No. How many? Oh, I have bought far too many. But I don't know, 15. Oh. But they are all pretty similar. I mean, there are some quality differences. I've thrown that slide out. But yeah, there are some which use 2 LDOs for both the digital and DAC reference supply. There are some that use a switching regulator for both, and then you can see the switching frequency modulating the DAC output. Of course, it's for a VGA monitor that doesn't care, but yeah. So the ones with 2 LDOs are actually the best for this abuse. Yeah, that's what I mentioned in the beginning, actually. At least it was in the slides, yeah. And this guy was motivated by this soft Tempest paper, which is really interesting. Yeah.
Okay, then thanks,
All right.
Steve.